So we're going to talk about thermodynamics. Normally it can turn into an entire PhD. Normally, if you're a physics major, you take probably 3 or 4 courses in thermo. We're going to do it in 2 lectures and should be good. So there's this law called the conservation of energy. And I'm quoting Feynman here. It's just some strange fact that we can calculate some number, and when we finish watching nature go through her tricks and calculate the number again, it's the same. So what's he saying? He's saying that it's kind of embarrassing. Physicists don't really have a good handle on what energy is. It's an abstract concept. It's not something that we can only see its effects. We can't see it. We can only see what it does. But we can calculate it, and we can calculate a system, how much energy is within that system, and then we can watch energy be converted from one form from another. We can watch some sort of change happening in nature, and we can calculate the amount of energy before the change and the amount of the energy after the change, and it's the same number. And no matter what kind of system we're looking at, whether it's something as simple as making a cup of coffee or something as grand as a planet or the entire universe. So if you look at a system, a thermodynamic system, a car, a human being, a cup of coffee again, a basketball bouncing, you can calculate how much energy it has, watch some change. And by change, I mean anything that you can sense with your senses or sense with an instrument. If you hear a sound, if you feel a temperature difference, if you see light, if something hits you, that's all energy being converted from one form to another. So when I feel wind, that's kinetic energy of air molecules flying through the air and then hitting my skin or a hair follicle, and I can feel that change in kinetic energy. If I feel heat that's coming off of this lamp that's above me, that's radiation energy. It's radiating in the visible and the infrared, not in the X-ray or gamma, so I'm not going to get sick or anything, but it's radiating energy, and I can feel that energy on my hand right here. And so anytime you feel something, sense something, see something, smell something, hear something, that's an energy conversion happening. And once you start to open your senses to that idea, you can notice that there's energy bouncing off, moving, converting all around you continuously. I mean, just you watching this lecture, you're hearing, I mean, my voice, it's insane, right? I'm breathing out some air, and it's gross, but I'm vibrating something in my throat, a larynx, I guess. And that's creating pressure waves that are then causing this microphone right here, some sort of membrane on the microphone to move back and forth. And so it's kinetic energy to kinetic energy. Kinetic means energy of motion, moving that membrane. And that membrane's moving back and forth, which is moving a magnet, which is causing a magnetic change, electromagnetic change in energy, which is causing a current to change in a wire. And then that current change in the wire is then amplified by circuitry within that microphone and then converted into ones and zeros, a digital translation of what that energy represents. Again, electrical energy sent into my computer and then sent from my computer via a wireless radiation signal to my modem. And then that's sent as an electric signal to some server, a bunch of electrical signals everywhere, and then sent via an electric signal to your computer, or to your router, and then turned back into radiation, and then turned back into electricity in your computer. And then that electrical signal is sent to a vibrating portion on your headphones or speakers that creates a pressure or kinetic wave. And now all of a sudden my voice is able to go back into your ears. So there's this insane amount of electrical and kinetic and pressure wave energy conversions throughout that entire system that's happening instantaneously everywhere. So once you start really thinking about it, there's these energy conversions happening constantly and continuously all around you. And no matter what, the amount of energy that system began with is the same. There's losses all along the way. There's heat being lost from that. So we'll talk about that in a sec. Let's do an example. So I'm going to stop sharing my screen, and now my just camera should be visible. Let's make sure we can see the floor here. All right. How much energy are you using right now versus sitting in a class lecture? If we were just, I'm now squatting for lecture. If we were just sitting in the lecture, I would venture to say we'd be using less. There'd be the amount of energy to run the lights in the room and the air conditioning, and that'd be about it. So if we were just looking at that control box or controlled system, we'd be using less in person. Because right now we all have our own computers and routers and lighting, et cetera, going. It was just a joke. Oh wait, guess it depends on how much stuff you're factoring. But if we start factoring in everybody commuting to campus, then this probably takes far less energy, especially when we start thinking about much longer commutes. Okay. Let's see, am I in the frame? Let's zoom up a little bit. All right. Catch my camera before it breaks. Tripod. Focus. See this? This is energy ball. Bye, Charlie. See this? Come on, focus. This is entropy ball. So here's energy ball. Right now, I'm pulling it from the center of the planet, and so it's gaining potential energy. It has a mass, and that mass is attracted to the center of the planet, and it's accelerated by the gravitational constant. So it has some energy now that I've pulled it up. Remember lifting the apple on the desk? That's like 1 Newton meter or 1 joule. So right now this has about a joule's worth of energy. If I drop it, this potential energy, gravitational potential energy, will be converted into kinetic energy, energy of motion. So let's try that. Right? So it had gravitational energy, now it's kinetic energy. And then that kinetic energy rebounds back as gravitational potential energy. So energy is conserved. Has 1 joule, gained a joule of motion, and then that motion stopped, and now it has a joule of energy again, it's potential energy. All right, so now I'm going to go with entropy ball instead of energy ball. They weigh the same, about the same shape, has a joule of energy, gravitational potential energy. Dead, just didn't do anything. Here, let's do it on the desk. There's my dog. She's greatly entertained right now. Sticker I need to throw away. Okay, so here's energy ball. Here's entropy ball. All right. So one violates the first law of thermodynamics. Energy is not conserved, or is it? What happened here? Where's my chair? What the hell is going on? All right. So energy ball was able to regain that potential energy back. Entropy ball didn't. So yeah, where'd this energy go in entropy ball? It's a piece of clay as a hint. Okay, energy was transferred to the floor, sound, shape, the air in the floor, heat, deformation, absorbed the energy. Yeah, something absorbed the energy. So the energy was converted from potential to kinetic as it was falling, and then all that kinetic energy turned into something else.
Was it going into reshaping it?
Yeah, so it did get reshaped. I mean, if I threw it really hard, it'd get flattened. First law of thermo, we'll get into it. It means that energy is conserved. Yeah, let me pull up the lecture slide again. Share screen. This, go to the next slide. Okay, so the first law tells us that energy is conserved. It tells you how much energy is in a system. The second law tells you that entropy is produced. It tells you the quality of the energy, how useful that energy is to societies. Okay, so for energy ball, where did the energy come from? Well, it came from gravitational attraction to the Earth. It came from me lifting it up in that gravitational field. The conversions that had occurred, it went from kinetic or potential energy to kinetic energy, back to potential energy, back to kinetic energy over and over again. And then an entropy ball, the energy went something else. We can draw a graph of this. Let's do that. Screen share. Let's grab this one. Okay, so yes, please draw. And let's have a solid line be energy ball and a dashed line be entropy ball. And this is energy over here. This is 1 joule. That's when I'm holding it a meter above the ground. And this is time. Let's call this time 1. This would be time 0 at the start. Time 2, 3, 4, etc. Now with energy ball, it does something like this. And let's just only plot potential energy. So the energy due to attraction to the center of the Earth. So it has 1 joule of potential energy. As it's falling, it's losing that potential energy because it's being converted into kinetic energy. And at time 1, it hits the floor, has no more potential energy at all. If we were to plot its kinetic energy on the same graph, it would go like this. Because now it has 1 joule of kinetic energy. Right at the very bottom of the fall, it's full of energy of motion, has no energy due to gravitational acceleration. And then it bounces off the floor and it gains potential energy again. All the while, it's losing kinetic energy. As right after it bounces, it starts slowing down, and gets to 0 at the top of its bounce. It hovers at 0 for a second. Yeah, so energy ball just goes back and forth. Kind of screwed up the time steps there. Whatever, this is 3, this is 4, this is 5, doesn't matter. Entropy ball has the same amount of potential energy at the start. It's hovering up in the sky. We drop it, it falls, and then it has no potential energy for the rest of the time. Its kinetic energy goes up. This is again entropy ball. Gains kinetic energy as it's falling, gets going faster and faster, hits the ground, and instantly drops to 0 kinetic energy too, and falls apart. So all of its energy was lost due to something. So let's explore that concept. And I've already seen the right answer in the chat. I'm going to open up the chat again. Okay, so absorb the energy. That's good. The air on the floor. So your senses told you that you heard a sound, right? There's sound. So some of that energy turned into pressure waves that scattered across the room. But the energy ball made a sound too. So, but it kept on going. So that must be a pretty small fraction of the energy. So energy ball did lose a teeny bit of energy to sound. Entropy ball lost most of its energy due to heat and deformation. So Jared got it right. Clay is a bunch of kind of plates, mineral plates. I forget if they're a hexagon or octagon or whatever. I'm a geophysicist, not a geologist. And those plates rub against each other. And you know, if you rub your hands together, they warm up, right? And so that 1 joule of potential energy turned into 1 joule of heat. Not a lot of heat, probably not anything I could feel. Recall that the cup of coffee was 0.04 kilowatt hours. So that's like 400th of a kilowatt hour. So maybe like, I don't know, 10 to the 4, 10 to the 3. I don't know, like 6, it'd be like 10,000 joules, I guess. So that's enough to make hot coffee. So if I threw this ball on the ground 10,000 times, it'd start to feel warm. That'd be pretty boring though. So there's something about that heat energy that was useless. It no longer produced any motion there. What if I gave it a tremendous amount of heat energy? Like what if I, blasted it with a Z torch? That's like a thing you can cut metal with. If I blasted that ball with a Z torch, gave it like, I don't know, a megawatt hour of energy, a tremendous amount of energy, would it bounce back up again? Would it start flying again? Could I make it do what the energy ball did? Get destroyed, it would take another form, it would melt, it would undergo some sort of transformation. Yeah, so it'd do something heat related, right? It would, the chemistry of this ball would react to the heat and do something, probably catch my house on fire. But it's never gonna bounce back up like energy ball. So there's something about the quality of that energy. Heat energy isn't nearly as useful as kinetic energy. And we'll learn that in 2 lectures from now. The most useful form of energy is electricity. You can convert that to nearly anything with near perfect efficiency. Whereas converting heat to other things is pretty lossy. It means if I want to convert heat back into motion, I have to trap that heat somehow. I have to trick it with something like a piston to turn it back into something like motion. Otherwise, it's just going to slowly spread out everywhere. And that's what the heat from this ball did. It spread out throughout the entire room and got absorbed into the walls, leaked through the insulation, whatever, went to outer space eventually. So it just slowly all leaks out. And so the first law of thermo tells us that energy is conserved. If there's any sort of system, the amount of total energy is the same as before as it was afterwards. We saw that very clearly with energy ball, the bouncy ball. Same is true with entropy ball, the ball of clay. It's just those conversions turn that energy into heat that spread out everywhere. The total amount of energy is still exactly the same. It just went all over the place and there's no way to get it back. And that's a qualitative description of entropy. Things fall apart, things diffuse, things spread out everywhere, and there's no way to put it back together again without using a tremendous amount of energy to do so. We'll talk about that next lecture. But this lecture, we're just focusing on what energy is and the first law of energy, that energy is conserved. Okay. Let's make this big again. So here's the forms of energy. How much heat does the bouncy ball generate? Something less than a joule. So it had about a joule of energy when it was a meter in the air. That joule of potential energy got turned into a joule of kinetic energy. Then we heard a sound. So some of that energy turned into sound, but most of it got turned into heat. So I'd say like 0.98 joules of heat. All right. So forms of energy. Maybe I'll let you guys figure this out in the chat. So we already talked about gravitational potential energy. That's when you pull something away from it, pull 2 masses apart. Normally, one of the masses is absolutely huge, like the Earth. Okay, so what are some other types of energy, some other flavors of energy? Elastic energy, yeah. So that's a form of mechanical energy. What else? I talked about all the different conversions. Electric, heat, chemical. Yeah, good, good, good. Thermal, heat, hydro. Hydro is actually potential energy. Well, it depends. It's energy of motion in the water, but the stuff that runs a hydro dam is potential energy, holding water up high and letting it go down a waterfall. Sound. Yep. So that's pressure energy, pressure, kinetic. What powers power plants? Chemistry, right? Coal and gas. Hydro, so that's potential. What else can make electricity? Nuclear. There you go. So nuclear energy. And then the last form I'm thinking about is light everywhere. The signals going to your router, the light coming out of light bulbs, out of the sun. Yeah, light. Oh, some people, said it. Yeah, so that's called electromagnetic energy. It's a huge spectrum of energy, all the way from really slow waves like radio waves, which are low energy, all the way through. Then you go microwaves, and then visible light. That's what we see. We see a small amount of radiation, a small amount of the electromagnetic spectrum. Incidentally, if you look at the entire electromagnetic spectrum, where do you think the sun might peak in its radiation? Does it peak in the radio wave? Does it peak in the visible 500 nanometers? Yeah, that's about right. So it peaks in the visible spectrum. So it's almost like our eyeballs evolved to see what the sun makes, and it's almost like leaves evolve to absorb what the sun makes. Just a thought. Okay. So forms of energy: gravitational potential, kinetic, chemical energy like in coal. So kinetic energy, we harvest it to make electricity using wind. Gravitational potential, we use it for hydropower, among other things. Chemical energy, so the wood that I heat my house with, or coal, that's all chemical energy. The gasoline in your car. Heat energy, so this is, it's not usually something we move. We do at Western, all the steam tunnels, we're moving heat to heat all the buildings, but usually you move something like a chemical, like natural gas, and then light it on fire and convert that chemistry into heat. Electricity, this is the most useful form of energy because it's really easily constrained. You just put it in a wire, it's got nowhere else to go, so you can send it to wherever you want it to go. Pressure, so this is pushing molecules together, gas molecules together. Nuclear energy and electromagnetic radiation, the energy of light, all the way from radio waves to gamma waves. Gamma waves, yeah. Okay, so those are all the different flavors of energy. There's other more exotic types, but this is what we're talking about in terms of society. All of these forms of energy, you don't need to write this down. This is not going to be on a test. This is later stuff, but I just want to express one point. Energy can be counted. Because of the first law, we know energy is conserved, and we're able to count it. We're able to tabulate it, both before and after any sort of conversion. So we have all these physical equations that we've derived through experimentation and observation that quantifies all these different types of energy. We're able to count it, add it up, and say something about the energy quality and quantity in a particular system. This is an important point. Energy is additive. So it's like mass. It's, if you have twice as much energy, you can add it together and you have twice as much energy. It doesn't add in weird ways. It's literally just additive, and that's very convenient. It makes the calculations a lot more simple. And so if you want to know the energy in a particular system, you just add all the different types of energy together. So in this example, we're adding internal energy, which I'll explain in a second, to kinetic energy, to potential energy, to electrical energy, to mechanical energy, etc. So what is this U? That's internal energy. It's describing the microscopic state of energy in a particular material or system. And so all the different atoms and molecules have their own little energy properties that you can add up. And when you sum them all together, you get something called internal energy. So when I heated up that water to make coffee, I was technically increasing the internal energy of that water. I was causing those molecules to vibrate more vigorously, for lack of a better word. Okay, so the internal energy it's known. If you take a course called statistical mechanics, you'll learn all about it. And it's the sum. That's what that sigma, that janky E means. It means the sum of all microscopic energy. And so let's look at a very simple molecule that represents most of our entire atmosphere. I think like 85% or something. And that's nitrogen. It's just two nitrogen atoms bounded together for a nitrogen molecule, and they have 3 bonds. And so those 3 bonds, they can translate. That just means move. So the whole molecule can move through the sky, through the air. It can rotate. It can be, rotating about itself in multiple ways. It could be rotating this way. It could be rotating this way. It has electronic energy. It could have a charge. It could be stripped of outer electrons or have an extra outer electron and be ionized. The energy of those chemical bonds, that's a very strong chemical bond. And if you were to break that, you'd have to input a tremendous amount of energy to break that bond. Same with CO2. It's a very strong bond between the carbon and the 2 oxygens. And it's so strong that when you burn just carbon and oxygen, when that bond is made, a bunch of energy is released. And that's how you get, your car to move, or a power plant to operate, or a fire to burn hot and bright. So separating that back out is going to take a lot of energy. So chemical bonds, nuclear, that should be bonds, not bands. So nuclear bonds, the things holding the neutrons and protons together within the atom itself, that's a lot of energy. If you break that apart, you get to make a bomb or a nuclear power plant. And then latent heat, and so that's a measure of the vibration. And latent heat is energy related to a phase change. If you're going from frozen state to a liquid state to a gaseous state, there's an amount of energy that needs to be inputted or taken out of to allow that change to happen. That's why if you have ice in a cooler, it just stays at 0 degrees C or 32 F, even if it's surrounded by water, because any additional heat that's going into your cooler goes into melting the ice, not changing the temperature of the water. What did U and the other symbol stand for? U is internal energy. So it's a sum of all the microscopic energy states within a particular substance. For lack of a better word, it's kind of like temperature, right? What is temperature measuring? It's measuring, in a sense, the internal energy of substance. But that's a pretty sloppy thing to say. So I'd get slapped if I said that in a statistical mechanics course. Okay. Yeah, sigma, this janky E, that means sum. Okay. All right, so if we were to balance, if we start thinking about calculating energy, how much energy something has, there's a few rules or maxims we need to know. So first law is just one example, and it defines energy. It's a simple statement of logic. It literally means it is what it is. It means that if you have something, you have something. And everything that it talks about is additive. And it's actually even simpler than that. So if we want to count how much energy we have using the first law, an accumulation of energy, if we're putting energy into a system, heating it, for example, the amount of accumulation will be the inputs of energy minus the outputs, plus production, plus destruction. And again, it's actually much easier than this, because can you produce or destroy energy? Can you magic energy? No. So the energy is conserved. That's what the first law says. So it's actually just, we can cross these out. It's just cross out production and destruction, and rate produced and rate destroyed. You can't magic energy. You can't create it and you can't destroy it. So if you want to increase the energy of a system, you have to get energy from somewhere else and pump it into that system. When we're calculating the amount of energy in a system, we usually draw something called a control surface. And that's just so we can isolate that system from other things in the universe. Because in reality, everything is open and exchanging energy continuously and constantly. But if we're looking at something simple like boiling a pot of water, then we would draw an imaginary bubble around that pot of water and think about its change of internal energy, its heat, for lack of a better word. And so if we were heating it up, we would think about how much energy we need to put into that pot of water to boil the water, for example. And we'd also have to think about the energy being lost, right? It's coming off the sides of the pot as heat. Not all of the flame or electrical element heating that pot is going to transfer into the water. It's going to go into your kitchen, et cetera, et cetera. And the change of energy within that pot of water will just be the energy before minus, or the energy after minus the energy before. That's E2 minus E1. And so the accumulation of energy in that pot, that delta E, the change in energy, will just be all the energy in minus all the energy out. I know this terminology and these symbols look confusing and scary, but it's really stupid and it's really easy. It's just saying the amount of energy when you boil water in a pot equals the amount of energy you put into the pot minus the energy that fell out of the pot. And the rate of energy transfer is just the change in energy over time, and the amount of energy over time putting in, and the minus amount of energy over time putting out. Now, this is calculus. Don't worry about this symbol. It just means a change in energy, change in something over a change in time. Delta means a very small change over a very small change in time. What is energy over time again? It's easy. Power. Yeah.
Power.
Yeah. So this, you guys already know this. You already know this calculus. You know it heuristically. You know it because you've experienced it your entire life. And you know that if you turn the burner up more, you're putting more power, you're increasing the power. So the change in energy over change in time is increasing, and you'll be able to create this accumulation of energy more rapidly because you have more power, more energy over time. Yeah, the D is a lowercase delta. It just means a really small change. All right. Let's skip over this crazy notation. Let's just talk about the three modes of heat transfer. Heat can be moved in three different ways. Conduction, you know that when you touch a hot or cold surface, the heat is being conducted into your hand if it's hot, and it's being conducted out of your hand if it's cold. That's what you're experiencing when that happens. Convection is trickier. It's heat being transferred due to changing densities of a substance. So think of, again, a pot of boiling water or soup, or a lava lamp if you've ever had any experience with one of those. Kind of a dated technology. But when most fluids, when you heat them up, they expand and become less dense. And so they float on the fluid, the colder fluid around it. And so that hot fluid moves up and floats, and the cold fluid sinks and then gets heated. And so that's a much more rapid way to heat something up using something like convection. And that's, in a sense, why a convection oven works a lot faster than a conventional oven, because you're moving the air around to increase the heat transfer from your oven into your food. Radiation, it's a scary word, but that's just describing like radiation that's harmful for you. You're being irradiated continuously and constantly by all forms of light, radio waves, your cell phone, and no, 5G is fine. Do not go crazy. Don't go down that rabbit hole. It's just radio waves, and so yeah, if you could see in all the spectrum, radio spectrum, microwave spectrum, that's what your Wi-Fi router is. You just see this constant, like, crazy busy scheme of waves everywhere. It'd be like you're a little ladybug floating in a big pool or the ocean. There'd just be waves constantly. All right. So radiation, you mainly experience it as visible light, sometimes as heat from your appliances, and then also your communications, Wi-Fi, cell phones, that sort of thing. More intense radiation you may have experienced if you get your teeth x-rayed, for example, something like that. Those are more powerful radiation waves, and so they can go through different substances, etc. Okay, So a transfer of energy, that's what work is defined as. Energy and work are interchangeable. Work is pure energy and completely useful energy is pure work. An energy transfer due to a force, either physical force or electromagnetic force, or a chemical force, that's work. And if we're talking just about a physical force in Newtonian mechanics, then a change in work equals force times distance. And work from position 1 to 2 is simply adding up all the forces and all the distances over a certain path. That's what that integral means. Again, don't worry about this. I'm just saying that this is something that's well known, well quantifiable, and this is the basis of thermodynamics. We can count how much energy there is. We can count all the different types of energy, add it up, and define systems well enough to be able to design computers or fly airplanes. Here are two animals. This one's doing work because it's actually moving something. This poor donkey, as cute as it is not doing any work because it's not moving. It may feel like it's doing work because it's certainly exerting itself. All that work is internal to the donkey, though. It's chemical reactions, etc., but it's doing no work on this entire system. If we drew a control system within the lungs of that donkey, we'd see work happening. Okay, let's do a quick calculation here. On board, so I gotta switch cameras. Turn on this camera, switch to it. I'm not getting any signal. All right, we're doing it on the electronic pad, even though my writing isn't as good. Wait, can I plug this other camera in? Technical difficulties. All right, well, it's worked in the past. Let's go back to the other camera and switch to the Photoshop board. Figure that out later. Okay, I'm still live. Share screen, Photoshop, share. Select all, delete, okay. Put that there. Let's get all right, let's get a new layer. Cool. So we have a surface. You guys able to see this all? Okay. And we have a ball and it's at height 1 and we're going to lift it to height 2. So just like we lifted energy ball and entropy ball, right? So we have to do work on that ball. We have to exert a force. And so that work from position 1 to 2 is going to be the integral or the path. And I know that you guys haven't taken calculus, or most of you haven't. So don't get scared by the language. It's just saying it's a path and it followed this path from here to here. Depends on the force adding up all the force that I exerted over that path over all the distance. Force times distance equals work for that path. We know that the force equals mass times acceleration. What's the acceleration that I'm fighting against here?
Gravity.
Gravity. Yeah, so the ball is being accelerated towards the center of the earth by gravity. So the force equals mg. So continuing this integral from position 1 to 2, force equals mg. So we can substitute mg over dx. Dx is all the teeny little distances all the way up here, adding them all up. Now in an integral, things that are constant, things that don't vary, you can pull out of the integral. And so we can take mg outside of the integral. Now we only have to integrate from 1 to 2 over dx. What's the integral of dx? Anybody know that? It's the fundamental theorem of calculus. If you add up all the little pieces of x, if you add up all the pieces of something, what do you get? Let's not even talk about integrals. If I chop a ruler into 100 pieces and I add up all the pieces together, I get something the length of the ruler. Yeah, so I just get the whole thing. So if we add up all those x's, then I just get x. So this is mgx evaluated from position 1 to 2. And so that equals mg x2 minus x1. That's that distance. 2 minus 1 is this space. What is that? That's how high it is. That's h. And so this just equals mgh. So the work from 1 to 2 equals the mass of the ball that I'm lifting multiplied by the gravitational constant g and how high I lift it. This is the equation for potential energy, or specifically a change in potential energy. This is what Newton calculated when that apple hit his head. So you all are as smart as Newton. It's not that hard. You look at the change in energy and you calculate it. So what I'm trying to say here is that all of these different types of energy can be calculated by observing systems and counting how much energy there was before and how much energy there was after, using fundamental rules like the first law of thermodynamics, that energy is conserved. So what happened here? This work was a transfer of energy. This is how we calculated that transfer. Calculation. And this here is an accumulation of energy. So somebody transferred energy into that ball by performing work. How much energy? Well, we can calculate that. It was mgh. How much energy was accumulated? Well, that's the change in potential energy, which equals the amount of energy that was transferred, because energy is conserved. What I want you to know for Energy 101 is that we can transfer energy, we can calculate how much gets transferred, and that's an accumulation or a loss of energy. Energy can be moved from one place to another. And this is something that we can do. All right. Next time, we'll look at transferring energy into a pot of boiling water, but I don't want to go over doing that calculation. That should be more intuitive than this. Questions, concerns, thoughts? Actually ended on time. Raised hand. Yes. Is G gravity? Yes.
Yes, I did have a question actually about the previous homework that was still left after watching the study session, when you have a moment.
Yeah, I'll get to Cody's question really quick. What forms of energy are we going to be focused on? Mainly electricity, because that's the most useful form of energy to society, and a little bit of electricity generation, burning things like coal and gas and making carbon dioxide. Um, Other questions about this lecture before we go to homework? What is M again? That's mass. That's how much the ball weighs. So recall, like an apple weighs 1/10 of a kilogram. So 0.1 kilograms multiplied by gravity, which is 10. And so 0.1 times 10 equals 1. And that's why lifting an apple 1 meter equals a joule. So an apple in this, if we lifted the apple, it would look like this. Work equals 0.1 kilograms multiplied by 10 meters per second squared multiplied by 1 meter high equals 1 kilogram meter squared per second squared equals 1 joule, because that's what a joule is in terms of standard international units. Don't be scared. We're just learning that energy is something we can count. That's all we're doing in this lecture. Is Q heat? Yes. Q is the symbol for heat. Does work unit always have sub 1, 2? No, that's just position 1 to 2. Sometimes you'll see it as work initial to final if we're talking about like a chemical change. Sometimes things are explicitly defined, like, you know, trying to launch a rocket or something. You'd say like work from Cape Canaveral to the moon. You know, it's just talking about where you're going to. We need to know that sigma stuff. No, you just need to know that you can add up all the different types of energy to calculate the total amount of energy in a system. Q is heat. Yeah, it's Latin for something. I forget. Wheat. Yeah, that's kind of obnoxious to say. Kind of dog do I have? Golden Doodle, of course. I don't know where she went. Franny. Lost my signal. Aaron, you can go ahead and ask about the homework from last time. Here's my dog.
Hi, Fran.
Franny. Hey, Franny, sit. Shake.
Go see Ernie.
All right. So Aaron had a question.
Yes. So for the conversions, this would fall under 3.1. Once we gathered all the information, we figured out the mass, we figured out the delta T, the change and everything. So the one thing I noticed, and you described it and I accept it, that we just multiply across the top. But if I take all that, so you've got joules times kilograms times the potential, which is joules over kilograms times delta T, which in this case we were using Kelvin, times Kelvin. If you plug it in and you plug in all those numbers, then I look at the equation and I ask myself, why am I not dividing 4,200 by the numbers that are under it, multiplying them together, dividing, then it all cancels out. No matter what I put in, everything's going to come out as 4,200. So it looks like we ignore the denominator. And I was wondering what that rule that governs that, so that if I have a future example, I don't try and solve it that way.
Yeah, I was confused about this sort of thing early on in my career as a physicist too. So you're confusing numbers tied to units with the units themselves. So let me get Photoshop, screen share. God, this is so much faster when I can just walk to a whiteboard. Where I need to get out of this so I can see. How do I get a new layer? Guess I'll just have to select all again. Select all. Delete. Put this back on the side. So each number is attached to a unit or units. Some things can have multiple units, just like energy. So what is a joule? So 1 joule is this, but the true units of what a joule is in terms of fundamental aspects of the universe, things like mass and energy and time, 1 joule equals 1 kilogram meter squared per second squared. And so in that equation, the heat capacity equation, delta E equals mass times the heat capacity of your material times delta T. I don't know why I'm writing with a mouse when I have a pen. The units of this are kilograms in terms of mass, and then the units of this number, this property of materials, its heat capacity, its propensity to change temperature with an energy input, is complicated. It's actually joules per kilogram per Celsius or Kelvin. That is the unit. That's the unit. That's the units of that number, and the unit of temperature is Celsius in this example. And so when you're plugging things in, so say you're heating up.
Guess I'll take him to the beach.
Say you're heating up 1 kilogram of water,
Okay.
and it has a heat capacity.
I'll come find you in a few minutes. Were you waiting? I didn't realize.
Say it has this heat capacity of joules per kilogram per C. That's the units. This number is attached to these units. And when I'm heating up like a kilogram of water, that water is attached to this unit, to the kilogram. I wouldn't put it here, or let me say 100 kilograms so it's not confusing. I wouldn't put 100 down here too. I'm only putting it here because I'm talking about the water here. I'm talking about the heat capacity here with all those units. And
Okay, so
and the temperature, the change in temperature, I just put it here because I'm saying this delta T is associated with 30 degrees in change in temperature, and it's associated with that. Whereas this C down here, that's talking about, that's a part of this 4200.
So treat the C sub P as one variable rather than each individual component, because I'm treating them like variables and trying to plug in numbers to them.
Yeah.
Okay.
Yeah, I mean, let me think of
that makes sense.
A stranger example like this. I don't know why my camera keeps on turning off. This fig tree behind me is green. That's one of its qualities. But if I had a green cup, I wouldn't say that they're the same thing. I'm saying that this fig tree is a plant. It's green. It's heavy, etc. It has multiple units attached to it. That might not be the best example. Maybe something like velocity. Velocity. So say you're going 50 miles per hour. This is your velocity. That's how fast your car is going. I'm describing the car. It's going 50 miles an hour. I wouldn't say the car is 50 miles. I certainly wouldn't call the car an hour. This is just, these units are intimately tied together as describing a concept called velocity. And so these units, joule over kilogram over Celsius, they're intimately tied together, and they're describing a phenomena called heat capacity. And this is a phenomena called temperature. Let's describe heat capacity qualitatively. What's it saying? It's saying so the heat capacity of water is
resistance to change.
Yeah. And what does that mean in terms of physical description? I'm saying that if I want to change its temperature, I have to put in this much energy. And it's also going to depend on how much stuff I want to change the temperature of. So if I want to change its temperature, I have to put in a certain amount of energy per unit mass, per the amount of temperature I want to change it. So if I want to change 2 kilograms of stuff, I'm gonna have to put in twice as much energy as I put in to change 1 kilogram of stuff. If I want to change that stuff by 2 degrees Celsius, I'm gonna have to put in twice as much energy than I otherwise would have for 1 degree. If I want to change 2 kilograms by 2 degrees Celsius, now I have to put in 2 times 2, 4 times as much energy to make that same amount of change in terms of temperature. It's tricky. So when you're plugging in numbers, think about the whole of what a variable or a constant represents. And so if I'm plugging in the amount of mass for something, for that one example, I forget how many gallons or whatever it was. So say it was like 50 kilograms. I'm only talking about mass in this instance. I'm not talking about heat capacity. So I would not put the 50 down there. But I'd totally see how you could get confused if you just plug in everything you know along with the units within a general variable. Then yeah, everything would cancel out, and you'd just be left with joules equals joules. It's also how you know the equation works, because you should get an answer with something with joules. So all the units should cancel out except for something equals something. What's going to change the number is the actual values ascribed to all those different units and collections of units. Whew. Good question. Bear in mind the quantitative, the mathy part of this class is pretty much up front, and the class will get much more descriptive and qualitative as we go on. We just need some formal language to describe what we're talking about in terms of energy. And so if this continues to be a struggle, don't worry. If you kind of have the idea that to change the temperature of something, you need to put in energy, and you need to put in more energy when there's more stuff and more energy when there's a greater change in temperature. That's all I'm really going for here. Cool. Let's see. There's 3 more comments in chat. Celtic cross background. Yeah, that is cool. Thank you, Professor Barnhart. All right, I'm going to head out. Thanks for the lecture. All right. Anything else? Agamas?
Thank you.
Alfine? All right, see you Wednesday.
See ya.
Thanks.
Bye.